Section 21.1 Radioactivity. To understand nuclear reactions, we must review and develop some ideas introduced in Section 2.3. First, recall that two types of subatomic particles reside in the nucleus, the proton and the neutron. We'll refer to these particles as nucleons. Recall also that all atoms of a given element have the same number of protons. This number is called the element's atomic number. The atoms of a given element can have different numbers of neutrons, however, so they can have different mass numbers. The mass number is the total number of nucleons in the nucleus. Atoms with the same atomic number but different mass numbers are known as isotopes. The different isotopes of an element are distinguished by their mass numbers. For example, the three naturally occurring isotopes of uranium are uranium-234, 235, and 238, where the numerical suffixes represent the mass numbers. These isotopes are also labeled using chemical symbols. Uranium-234, 235, and 238. The superscript is the mass number. The subscript is the atomic number. Different isotopes have different natural abundances. For example, 99.3% of naturally occurring uranium is uranium-238. 0.7% is uranium-235, and only a trace of uranium-234. Different nuclei also have different stabilities. Indeed, the nuclear properties of an atom depends on the number of protons and neutrons in its nucleus. A nuclide is a nucleus with a specific number of protons and neutrons. Nuclei that are radioactive are called radionuclides, and atoms containing these nuclei are called radioisotopes. Nuclear equations. Most nuclei found in nature are stable and remain intact indefinitely. Radionuclides, however, are unstable and spontaneously emit particles and electromagnetic radiation. Emission of radiation is one of the ways to which unstable nucleus is transformed into a more stable one with less energy. The emitted radiation is the carrier of excess energy. Uranium-238, for example, is a radioactive, undergoing a nuclear reaction in which helium-4 nuclei are spontaneously emitted. Helium-4 particles are known as alpha particles, and a stream of these particles is called alpha radiation. When a uranium-238 nucleus loses an alpha particle, the remaining fragment has an atomic number of 90 and a mass number of 234. If you look at the periodic table, you'll find that the element with an atomic 90 is thorium. Therefore, the products of uranium-238 decomposition are an alpha particle and a thorium-234 nucleus. We represent this reaction by the following nuclear equation. When a nucleus spontaneously decomposes in this way, it's said to have decayed or to have undergone radioactive decay. Because an alpha particle is involved in this reaction, scientists also describe the process as alpha decay. In equation 21.1, the sum of the mass numbers is the same on both sides of the equation. Likewise, the sum of the atomic numbers on both sides of the equation is equal. Mass numbers and atomic numbers must be balanced in all nuclear equations. The radioactive properties of the nucleus are independent of the chemical state of the atom. In writing nuclear equations, therefore, we're not concerned with the chemical form, element, or compound of the atom in which the nucleus resides. Types of radioactive decay. The three most common kinds of radioactive decay are alpha, beta, and gamma radiation. Table 21.1 summarizes some of the important properties of these kinds of radiation. As we've just discussed, alpha radiation consists of a stream of helium-4 nuclei known as alpha particles, which we denote as helium-4 or alpha-4. Beta radiation consists of a stream of beta particles, which are high-speed electrons emitted by an unstable nucleus. Beta particles are represented in nuclear equations by the symbol electron to the 0 or sometimes beta to the 0. The superscript 0 indicates the mass of the electron is exceedingly small compared to the mass of a nucleon. The subscript -1 represents the negative charge of the particle, which is opposite to that of the proton. Iodine-131 is an isotope that undergoes beta decay. You can see from equation 21.2 that beta decay causes the atomic number to increase from 53 to 54. Therefore, beta emission is equivalent to the conversion of a neutron to a proton, thereby increasing the atomic number by 1. Just because an electron is ejected from a nucleus, however, it should not think that the nucleus is composed of these particles any more than we consider a match to be composed of sparks simply because it gives them off when struck. The electron comes into being only when the nucleus undergoes a nuclear reaction. Gamma radiation, or gamma rays, consists of high-energy photons, that is, electromagnetic radiation of a very short wavelength. It changes neither the atomic number or the mass number of a nucleus and is represented by gamma 00, or merely gamma. Gamma radiation usually accompanies other radioactive emission because it represents the energy lost when the remaining nucleons reorganize into more stable arrangements. Generally, the gamma rays are not shown when writing nuclear equations. Two other types of radioactive decay are positron emission and electron capture. A positron is a particle that has the same mass as an electron, but an opposite charge. The positron is represented by electron 0. The isotope carbon-11 decays by positron emission. Positron emission causes the atomic number to decrease from 6 to 5. The emission of a positron has the effect of converting a proton to a neutron, thereby decreasing the atomic number by the nucleus by 1. Electron capture is the capture by the nucleus of an electron from the electron cloud surrounding the nucleus. Rubidium-81 undergoes decay in this fashion, as shown in Figure 21.6. Rubidium plus orbital electron is krypton 3681. Because the electron is consumed rather than formed in the process, it is shown on the reactant side of the equation. Electron capture, like positron emission, has an effect to converting a proton to a neutron. Table 21.2 summarizes the symbols used to represent the various elementary particles commonly encountered in the nuclear reactions. Neutron is N to the 1. Proton is H to the 1 or P to the 1. Electron is E to the 0. Alpha particle is He to the 4 or alpha 4. Beta is E to the 0 or beta to the 0. And a positron is E to the 0.